So yeah, so today I actually want to hope you, to generate a discussion amongst the group on the call. That's my primary objective. We'll manage it somehow without the chat room. I want to be a bit of an instigator here, and as well as try and facilitate a discussion, I want to try and instigate a bit here, and perhaps say some things that are not beyond the pale, but perhaps a bit incentive in nature. And to do that, I want to start with the energy transition context that Sarah just touched on. And then I want to look at what energy problems we can solve with geothermal. And then given that, what should our priorities be on the island of Ireland? And given those priorities, what help do we need from policymakers, from the public and from the private sector? So our energy transition challenge isn't just about emissions, is my first point. Our energy consumption trajectory is actually unsustainable for more than one reason. Now, emissions affecting greenhouse gas warming is certainly important, and this picture's for the Republic of Ireland only, and it shows the four main sectors of emissions. There's agriculture, there's energy power generation, there's heat in residential, industry, public services, commercial buildings, and there's transport. And I think it's fair to say that there's progress on mobility, transport, electrification of transport particularly, and there's process, particularly in Ireland, with the greening of the electrification grid. But it's not just that. It's also about affordability. So the graph on the left shows the power density of different energy sources, and it shows that geothermal is in the same mix of power density as wind and solar here in the middle of the chart. But it also shows that compared to gas, oil, coal, and nuclear, these renewable energies are actually much lower power density than fossil fuels. That said, over the last few decades, the cost of fossil fuels, particularly oil, and now natural gas, I would argue, has been creeping up and up. So, for example, in my career in the oil and gas industry, when I started, $16 or $20 a barrel would be happy days. And less than 10 would be, pink slips and P45s. Nowadays, happy days in the oil and gas industry is $80 a barrel, and today's $120 a barrel is exceptionally good. But this is a result of us having to put more and more effort into extracting oil. We're having to put more energy in to get the same amount of energy out. And this is captured on the right-hand side of with an energy return on investment graph, where domestic oil in the United States, for example, in the 1930s, you'd get 100 barrels of oil out for every barrel of oil invested in extraction. By 2005, it was down below 40 to 1, and shale oil and gas is probably about 5 to 1. There's debate about what the magic number needs to be, but it's more than 10 in order for the economy as we know it to thrive. So this is another reason why we need to get ourselves off of oil and gas, is that it's becoming increasingly finite as a resource and too expensive for our economy. And then the third reason is security, reliability. And this is illustrated for decades by oil. You know, when a sniff of a crisis affected oil price the next day or the same day. And now that gas has joined its elder sibling as a global commodity with LNG and far-reaching pipelines, gas is the same problem of supply-demand tightness and relaxation, of geopolitics, of trader anxiety, and of course, unfortunately now, the cost of war and conflict, of course, in this case, in the Ukraine. And Ireland is right at the end of a very extensive pipeline infrastructure across Europe. Not all the gas is coming from Russia, of course, where UK only takes about 1 or 2% of Russian gas. Most of it comes from the North Sea and some LNG imports. But the island of Ireland is at the end, has no LNG import, and is at the end of an infrastructure that has 3 pipelines in the Irish Sea, all coming from a single terminal in Muffet in southwest Scotland. And so that represents a security risk as well as a price risk, because we're dependent on the price structure and price swings in the rest of the infrastructure. So then, so this is all captured in the classic notion of the energy trilemma. And this is the way I like to think about the energy transition, that we need to not just solve for sustainability, but we also need to solve for affordability, particularly for those that are already impoverished in terms of energy. And we need to solve for security. The energy that we use needs to be reliable. It needs to be secure in supply. And I've put a picture here of Gordon Lyons, the Minister of Energy for Northern Ireland, holding up the report published late last year from the Energy Strategy team in Northern Ireland. And I've given them 2 thumbs up because they've got the energy trilemma pictured on the front: secure, affordable, clean. That's what we need to be about. So then, so how do we go about this? What we're starting to get into what problems we're trying to solve. This is a Sankey diagram, or energy flow chart, that we put together for the whole island of Ireland, and this is using 2018 data from both Northern Ireland and the Republic of Ireland. And what this shows is the flow of energy from source or primary energy requirement from the left-hand side through electricity generation here in the middle, and then over to the right-hand side where it's used in different sectors. And then in the far right-hand side of the diagram, what I've done is illustrated using some data from Ireland and some data from other countries about how energy is used or not used. And so you can, for example, oil, all of Ireland's oil and petroleum products are imported, of course, and most of it is used in transport, obviously, but a fair amount is still used as heating in industry, in residential and service buildings. I'll also take gas. Natural gas contributes to heating, as we know. It also contributes to generation of electricity. But actually, this illustrates the significant inefficiency of electricity generation using thermal resources, because in converting gas into electricity, there's a significant inefficiency and conversion loss here in the middle. So by the time you put that all together, we actually end up using in active energy work only about 1/3 of the energy that we've sourced originally from the primary energy supply, and 2/3 is literally wasted in transformation or transmission or direct use. It goes up the chimney, out the exhaust pipe, or a noisy engine, or other such wastes or rejections of energy. Now that's significant because I think the first part of energy transition is actually being much more efficient and demand focused on the use of energy. And electric vehicles are actually a good illustration of that. Electric vehicles are very efficient in using electricity, using energy, closer to 95% efficient. And they also allow you to put the point sources of emissions back to 1 or 2 point sources rather than millions in the terms of vehicles. So that's job number one with the energy transition, is to radically reduce our demand through re-engineering our systems and improving efficiency. And it's not just about technology and engineering, it's about societal norms and expectations. I've picked on SUVs here. There's a stat going around about if SUVs were a country, they'd be the 6th biggest emitter in the world. People are still buying SUVs and running around in them, even though we are doing a better and better job of hybrid and electric plug-in hybrid sales in this is Republic of Ireland data in this case from last year. But we need, there's a sort of a way of changing our attitude and our cultural norms that Range Rover Sport is not the preferred option anymore. It's go get yourself a Tesla Model 3 if you want something fancy, but much more sustainable and as an option. So then on to geothermal. Like we know, everybody on this call, I think, will be familiar with the science of geothermal. This is a map put together by Helen Doran, and it shows the geothermal hotspots of the world associated with plate tectonic boundaries. And it also shows some of the volcanic hotspots away from plate tectonic boundaries. The most significant thing for me is it shows that most of the world is kind of bog standard 25 degrees centigrade per kilometer geothermal gradient. And that includes the Irish and British Isles right up there towards the top. So in other words, if you can make good use of geothermal in Ireland, it means you can make good use of geothermal most everywhere in the world. Meanwhile, we do know that geothermal is being used around the world. There's electricity generation from lower temperature resources, 80 to 180 degrees centigrade temperature, but they typically are very close to the surface, less than a kilometer close to the surface. The big energy, the 50% of the energy, geothermal energy that's used, is actually used in combination with heat pumps in domestic, commercial, industrial settings. And then there's some direct use. So this is to give you a flavor, or give us a flavor of what might be possible here in Ireland. A reminder of the principal archetypes. There's 2 geothermal resources, I would assert: shallow, less than 500 meters or thereabouts. That are typically, those resources are used in combination with heat pumps. It's also a fantastic storage medium, shallow geothermal, which is important and we'll touch on again. And the second one is deep geothermal, typically more than 500 meters, actually considerably more than 500 meters in settings like ours. And that direct heat is for power generation or direct use of heat. Basically 2 types of geothermal system. I'm really oversimplifying this, I know, but one I would say is open loop, where fluids are being exchanged from the well into the rocks and back again. And the second is closed loop or advanced geothermal systems, AGS, where there's no fluid exchange and instead conduction is used to harvest the heat. And on this BGS diagram, the shallow systems are on the left-hand side, and the deep systems are on the right-hand side. So now to problems. So I've got three problems to posit that we could solve or address with geothermal. The first one I'm going to point to is the issue of variability and intermittency on wind and solar. Just recently, Ireland ordered or did an auction on 9 new power plants, gas generation, apparently 1 or 2 of them to be hydrogen ready, all about them being peaker plants. And this is because even when you put more and more wind and solar into a regional or national grid, you still need dispatchable thermal capacity to make cover off shortfalls when the wind isn't blowing for a number of days, or the sun isn't shining for a number of days. And I've put a dirty dozen here of different mechanisms of providing storage of electricity or storage of energy in the case of thermal, and none of these are really at the moment up to covering off periods of days and weeks. Batteries can do very well for a few nanoseconds, for seconds, minutes, and a few hours, but they can't do as yet. They can't do days and days and weeks. And so the romance about geothermal power is, can you use geothermal power as a dispatchable base load to cover off and complement wind and solar? And an answer for Ireland is unfortunately no, or at least not for some time. It's really hard in Ireland because the temperatures required for any reasonable efficiency in power generation are at substantial depth. So although binary organic Rankine cycle turbines can generate electricity at 80 degrees centigrade, they really need to get to about 120 degrees centigrade fluids before you've got any reasonable significant efficiency, and this still only 15%. And then when you combine that with drilling costs, and this is a US data, the blue line, the blue dots is US and Department of Energy data, and it shows you that to get to the temperatures that you require in Ireland, you're talking quite a lot of money, $15 million per well or more, and the economics just don't make sense at that. So I'm just going to pause for a moment before I address the second problem and just do a little sidebar on heat pumps, just to make sure that everybody falls in love with heat pumps just the same way I have and Causeway GT has. Heat pumps are marvelous pieces of engineering. They actually have efficiencies greater than 100%. And how they do that is they soak up through a heat exchange heat from a source, and they through evaporation, compression, and I've lost the word. It'll come back to me, but through the heat pump process, the temperature is elevated, and more heat energy is delivered to the target sink than is used as electricity. So in other words, for 5 units in this particular model, for 5 units of electricity doing the work of the heat pump, the compression piece, and soaking up 10 units of heat from whatever medium, in our case geothermal, 15 kilowatts of heat are delivered. So the COP, the coefficient of performance of the heat pump in this case, is 3. Heat pumps are actually able to do much better than that, particularly where you're not having to elevate the temperature so much. So why am I doing this little sidebar on heat pumps and COP? So here's a typical sort of ground source setting, everything from freezing conditions in the subsurface to typical 12 degrees centigrade temperatures. To get to a sink temperature of 55 or 60 degrees centigrade, which is usually the minimum requirement to eliminate Legionella, you need a source temperature of 12, COP of 3 gets you to the required delivery temperature. Then over in this right-hand chart, I put the same COP of 3 and I track it up along the y-axis of levelized cost of heat. And what you see here is that if I have a expensive electricity at 14 pence per kilowatt hour, my gas boiler is actually is more cost efficient than my heat pump. But if my electricity cost comes down to 10 pence per kilowatt hour, my heat pump is now competitive. In other words, the one of the primary factors for the competitiveness of heat pumps is electricity price and how that relates to the coefficient of performance of the machine itself. So then problem number 2, I'm going to take problem number 2 is heat above 80 degrees centigrade. So this is heat that would be in low-grade industrial processes and high-grade industrial processes. I don't think we can do much for in the very high temperature regime, like in terms of metals manufacture, aluminum or steel. But I do know that we can do a lot of good and a lot of elimination of fossil fuels in the lower temperature range from 80 to 140. How's that so? Well, for example, in the northeast of the island, there's some super opportunities of open loop permeable reservoirs where, for example, the geothermal gradient is a little bit elevated in the northeast as well, and you can see 50 degrees centigrade at 1.5 kilometers depth. Using industrial scale heat pumps, megawatts in scale, a 50 degree centigrade source temperature is really useful when you put a heat pump on top of it, and it can be elevated up to 125 degrees centigrade, which is a bit of a magic number because once you get there, you're able to generate steam, which is a very common fluid used in many different manufacturing and industrial processes. So what I'll argue to the group on the call is that one of our priorities is to make a demonstrator of this happen, and probably County Antrim and the region is probably the favourable place to do this. But that's not all. In Causeway GT, we're pretty well focused, not exclusively. We will consider open loop, but we're pretty focused on closed loop because although it's got the slowness of conduction to deal with, its advantages are significant in terms of not needing porosity, not needing permeability, not needing to exchange fluids, not needing to worry about induced seismicity, not needing to worry about contamination of aquifers or bringing geothermal brines to the surface, and never ever having to mention the word frack in polite company outside of the state of Texas. So we're focused on closed loop. What can be done with that? So there's a recent study that's just been released beginning of the year from the Cornell University. It's Beckers et al. Are the authors. They ran a number of interesting scenarios, simulation models on closed loop systems. And what they found was the levelized cost of heat from these different closed loop scenarios was the average or the mean was $46 per megawatt hour. And that's quite attractive. Whereas for electricity, it was over $800 per megawatt hour. And this is essentially the inefficiency of low temperature electricity generation coming through in these costs. So they agree that for lower temperatures, power generation is very challenging, is the phrase they used. but I have to say they did not include heat pumps in their study. They did mention, but they did not include it in any of the analysis. Ongoing work in Causeway GT, where we've been doing some modeling. Alison Isherwood has been leading the charge on this, and understanding the nature and sensitivities and controls on conduction-only systems, closed loop. And we've been examining some economic sensitivities that actually support the findings of the Cornell study and present a credible pathway to commercialization of 100 degrees centigrade plus heat. There's further work ongoing, and including some work led by Professor Neil Hewitt in Ulster University, where we were awarded a case grant for that work last year, and we're planning some pilots to test this technology. And if we can make that work, we can do a lot of decarbonization of lower grade industrial heat. And then final problem is everything else. Now this is my chart of the distribution of heat use in Ireland. It looks a bit different from the recent SEAI study, and I'm still trying to understand why they've come up with a bigger proportion of higher temperature heat. But suffice it to say that more than half, and I think considerably more than half of our heat that we use is actually less than 80 degrees centigrade. Space heating, water heating, space cooling as well. And this brings us right into the domain of heat pumps and geothermal heat pumps specifically. Here is some data from the SEAI report. It's a really good report. There's a couple of things I'd quibble with, but some really good information, good insight. So this one here is for residential, commercial, and public service buildings, a breakdown of the suitability of different technologies for heating and cooling these parts of the built environment. And here are air-sourced heat pumps and geothermal heat pumps, or ground-sourced heat pumps here in the towards the left. And as you can see, residential, a lot of potential to do good with heat pumps, be it ground-sourced or air-sourced. In commercial, they conclude that commercial buildings are actually often leakier than residential buildings. That's one of the things I'm kind of scratching my head about, because that came as a bit of a surprise to me, to be candid. But again, the potential with some fabrication improvement in commercial buildings is huge. And then similarly, then public buildings, hospitals, large schools, libraries, government buildings. Lots of potential there. And then on the right hand side, I've taken some older SEAI data on the costing of different residential heating mechanisms, and geothermal ground sourced wins the day in terms of efficiency. Also very low emissions, of course, particularly as the electricity used gets cleaner and cleaner. But solar thermal is good as well, and obviously air source heat pumps are good as well. So an interesting combination there between cost competitiveness, emissions reduction, and on the left hand side, suitability. So I actually think, that we ought to be persuading policymakers to change the dimension on the use of shallow geothermal heat pumps. Here, for example, is in the case of commercial and industrial lower temperature heat. There's a cartoon picture of Microsoft's expansion of their campus in the state of Washington in the Northwest United States. It's plus 10 megawatt thermal heating and cooling, and it's all served by a geothermal system down to about 150 meters depth, both storage and borehole heat exchangers, and a vast network of heat network of pipe work supplying it. And very low emissions product as a result. On the right-hand side, there's a couple of maps, one from GSI, which shows that in the Republic of Ireland, the suitability for closed loop is very high. In other words, there's only about 5% of the country that is not suitable for closed loop geothermal systems. And in Northern Ireland is actually a similar picture. I don't want to embarrass Rob Rain, but the map is really good. But the color coding of the scale is misleading because 1 watt per meter per Kelvin is actually really good conductivity for a closed loop system. And 0.5 or 0.25 would be seen as okay. So in other words, Northern Ireland's like the rest of the island. It's highly suitable for closed loop. And indeed, Northern Ireland also, because of shallow aquifers, like the Sherwood Sandstone, is also highly suitable for open loop systems, which can be more efficient than closed loop. So a blessing of shallow geothermal resource in the island to use at kilowatt scale or at megawatt scale for heating and cooling. So why aren't we doing this already? I hear you ask. And the answer seems to be a combination of a number of different factors. A good way to get to the answer is to compare ourselves to other countries with higher uptake of geothermal, and the poster child is Sweden. And it's an interesting poster child because, according to Helen's map, Sweden, as you might expect if you're a geologist, is actually lower geothermal gradient than Ireland and Britain, and certainly lower than some other countries in Western Europe. But having said that, Sweden is one of the highest, if not the highest, geothermal energy user, and the vast majority of that's heat pumps, ladies and gentlemen, at the scale of kilowatts to megawatts that I've been describing. So the little cool colors over in Ireland and Britain in terms of geothermal usage, we need to fix that, right? The reasons for slow uptake seem to be about ambition. Sweden has been decades on the journey of decarbonization and are blessed by renewable resources like hydro, I have to say. I think the second thing about awareness, and its cousin myths and legends. People say things like, "Well, heat pumps won't work on leaky homes," and the retrofit's too expensive, or things like that. There's a capability issue. We have some expert resources on the island that know about heat pumps and shallow geothermal, that's for sure. But I actually think we need more. We need more organizations, companies, and capability on this matter. I'll get to a little bit more detail on this next point, but commercial developers and operators of geothermal heat systems are going to need some assistance on pricing and incentives and security or surety of their supply. In other words, if I'm putting a geothermal heat system underneath a commercial building, I need to know through a power purchase agreement or heat as a service contract that the owner of the building is going to be using my heat, for 15 or 20 years, for whatever the duration of the agreement and the project actually is. So here's a little bit more detail about electricity pricing. This is data from Eurostat, and on the in both charts, what I've done here is I've divided the price of electricity by the price of gas. So this is the electricity gas price ratio. The difference between the two maps is on the left, I've included all the taxes, which include climate change levies, social obligations, different types of infrastructure taxes and stuff like that. And on the right-hand side, it's without the taxes, so it's like the wholesale price. And what you can see here is that not unexpectedly, Sweden has a very low ratio, significantly less than the magic number of 3 from coefficient of performance of heat pumps, which we addressed earlier, as does Finland, and a number of other countries are in the right area below 3. The UK is up at 6.1 and Ireland's at 4.8. And then you switched over to the right-hand side, and you can start to see, well, what impact does taxation have on this price imbalance? And it turns out that in many European countries, ironically, things like climate change levies and other similar taxes are actually levied on electricity, not natural gas, which is a bit counterintuitive, I know, but it's true. That's not the case in Ireland. You'll see that the 4.8 plays 4.5 shows that the difference isn't so great. By the way, this is for non-household energy. In fact, for household energy, the ratio looks a lot better in the Republic of Ireland. But it is true in the UK. There is a heavier bias towards taxation on electricity than natural gas in the UK. So, you know, the conclusion of this is that we need some help on this to make geothermal heat pumps, or any type of heat pump, be they water source from mines or rivers or air sourced. We need some help, I think, on electricity costs. Put another way, we need to find a way to change the supply price of about 5 pence per kilowatt hour into something closer to 6 or 7 pence per kilowatt hour, rather than the 20 plus pence per kilowatt hour that we're paying now as consumers. So quite a restructuring of the electricity price market. So I'm coming to the end of my presentation. This is a chart we put out in a blog a couple of months ago, trying to color code our sense, Causeway GT's sense of readiness. And basically what we're saying is we're good to go on domestic use of geothermal. Similarly, on large buildings and low temperature industrial, we're good to go. But we probably need some help with electricity costs, some help with permitting and legislation. And of course, as we go deeper, we'll need to make sure we clarify the ownership of heat at depth, the drilling rights and so forth. And then on the right hand side, I've color coded most of the electricity generation as orange, and something for the future when our American colleagues or North American colleagues have figured out how to drill 5 kilometers for £1 million rather than 15 million pounds. So then I think the next slide is my last. Yeah. So Sarah, this would be my segue into the discussion. So this is my view on priorities, policy support, public and private sector. I'd really love to hear the input, questions, of course, about my presentation, but discussive questions on these priorities. So I'm saying, let's get after geothermal heat pumps, small and large scale, deploy. Let's get after it. Let's get engaging with the public and the stakeholders on this and get their support. It's a decarbonization, low-hanging fruit opportunity. Just let's get going on it, and contribute to technology development on this where it makes sense to Irish needs and the resources and skills and expertise that we have on the island. In terms of policy support, we certainly do need clear and efficient regulation and regulatory process. We need some help with price structures, some help with heat network and the equivalent of heat power purchase agreement structures. I think there's a super opportunity for both jurisdictions to put their public buildings and land up for tender for demonstrators and pilots. And we should do with some funding from government to support those pilots and demonstrators in both jurisdictions. Private sector, there is a wonderful opportunity for some entrepreneur to put a company together that provides domestic consumers a one-stop shop, hard to say on a Friday morning, to fix home heating, in terms of fabric improvement. What type of heat pump do you need? Is it air source, ground source? Have you enough space in the back garden? All of that stuff. Help people through grants and legislative incentives and how to apply for them. In commercial property and lower temperature industry, I think we need those folks to just start asking, well, why am I not using geothermal as one of my components of my energy mix? Rather than asking why I should use it. Private sector is. We know that the private sector, in terms of project finance, is really dying to get into this at actually very low single-digit returns to finance these commercial projects. So there's some finance and some money available to support this as well from the private sector. Policy support I've mentioned. Finally, then public. We need to engage, educate, inform, and inspire the public. I spoke yesterday to some pretty smart people here locally in Lincolnshire, where I'm speaking from, in county council and local enterprise partnership. They'd never heard of geothermal. And Lincolnshire is actually pretty similar to the north part of Ireland in terms of both shallow and deep geothermal resource. They're very enthusiastic and very welcoming of the opportunity. It's just a blind spot for many people. So we just need to keep up the good work in terms of education and information. We do need to be clear about readiness, affordability, and security of the solutions, and the risks if there are risks. We don't need to be talking about fracking. That we don't need to go fracking to deliver this. So we don't need to be, talking too much about things that are concerns to other countries. We can do a lot of good with our geothermal resources without needing to address those risks. And there's also an opportunity to consider job creation and competency and capability creation, both for technical engineers, installation and maintenance and operation, but also for masters and PhD type engineers and geoscientists to be involved in this fledgling and growing industry. And my Causeway GT colleagues and I are firmly set in the vision that we want Ireland to actually become a centre of excellence for geothermal energy in the future.